Welcome to this lecture on Python data and text essentials. In this video, we'll focus on strings, collections, formatting, and numbers. These are the foundations of working with textual and structured data in Python, and they're critical for building real-world programs. Python offers a wide variety of built-in types, each designed for specific use cases, such as storing ordered data, creating mappings, or ensuring immutability. By the end of this lecture, you'll understand how to work with strings, format them cleanly, manipulate lists, tuples, sets, and dictionaries, and perform both implicit and explicit type conversions. We'll also touch on binary numbers, which underlie all computer storage. This video builds on what you already know about Python basics and extends it to give you tools for managing data in flexible and powerful ways. Python data and text essentials: strings, collections, formats, and numbers by the programming professor. Let's look at the outline of what we'll cover. We'll begin with string basics, where we'll learn how strings are created, indexed, and manipulated. Then we'll move into string formatting, focusing on f-strings and format specifiers that make output clear and professional. Next, we'll study lists, one of Python's most versatile data types, covering creation, indexing, mutation, and useful operations. Tuples will follow, showing us immutable collections, including named tuples for added readability. Sets come next, where we'll learn about uniqueness, membership tests, and set operations. Dictionaries will be discussed as key, value mappings, and how to add, modify, or delete entries. We'll then look at a comparison of all the common container types before moving into type conversions, both implicit and explicit. Finally, we'll wrap up with binary numbers to understand how computers represent data. Strings are one of the most common Python data types, and they represent text. A string literal is text written directly in the source code surrounded by quotes, like hello or world. Strings are sequence types, which means each character is ordered and accessible by index. For instance, in the word Trish, the letter T is at index 0, R is at index 1, and so on. Strings can be stored in variables or captured from user input. An empty string contains 0 characters and is written with 2 quotes back-to-back. In practice, strings allow us to represent names, locations, and messages within a program. The examples in the slide demonstrate creating strings, storing them in variables, reading one from user input, and working with an empty string. A common operation with strings is determining their length and accessing individual characters. Python provides the built-in function len to return the number of characters in a string, and this works with other sequence types too. Because strings are ordered, you can access characters using their index, which always starts at 0. For example, in ABC, the character A is at position 0, B at 1, and C at 2. Negative indices work as well, counting from the right side, so -1 would refer to the last character. On the slide, the examples show how len gives the length of the string Python, and indexing allows you to select characters like the first, third, or last one. These features make strings flexible and easy to manipulate when working with text. It's important to understand that strings in Python are immutable, meaning they cannot be changed in place. If you attempt to reassign a single character, Python will throw a type error. To change a string, you must build a new one and reassign it to the variable. This concept is shown on the slide where a name string is updated by creating a new string with an altered first character. Another common operation is concatenation, where you join strings together using the plus operator. Concatenation doesn't modify the originals. It produces a new string. You can concatenate string literals or variables, and you must convert numbers to strings first using str before combining them. The slide examples illustrate these principles by creating new strings and building addresses from numeric and text parts. Formatted string literals, or f-strings, make it much easier to build output that includes variables and expressions. Instead of concatenating strings manually, you can use an f-string by placing the letter F before your quotes and putting placeholder expressions inside curly braces. During execution, Python evaluates the expressions and replaces them with their values. For example, if you have variables storing a name and an age, you can create a message that inserts those values directly into a sentence. This makes code more readable and avoids clutter from multiple plus signs or calls to str. On the slide, the examples show how f-strings can include variables, arithmetic expressions, or even debugging with the equals sign, where Python displays both the expression and its result. F-strings are the recommended way to format output in modern Python. Format specifications extend the power of f-strings by allowing you to control exactly how a value is displayed. Inside the curly braces, a colon separates the expression from the formatting instructions. For example, num.2f formats a number with 2 decimal places. You can also add leading zeros, control alignment, or change numeric bases. Presentation types determine whether the value appears as an integer, floating point number, percentage, binary, or hexadecimal. On the slide, examples demonstrate formatting 4 as 4.00, padding it with zeros, aligning it within a set width, or showing its binary representation. These formatting tools give you professional-looking output and ensure numbers are presented consistently, which is especially important when displaying results in reports, tables, or user interfaces. Lists are Python's most flexible container type, and they are used to group related values into an ordered collection. A list is created with square brackets, and each item inside is called an element. Lists are mutable, which means you can change, reorder, or remove elements after the list is created. Because they are sequence types, lists support indexing that starts at 0, so you can access elements by position. An empty list is written as 2 square brackets with nothing inside. On the slide, examples show creating lists with numbers and strings, printing elements, and creating an empty list. Lists are one of the most common tools in Python because they allow you to reduce the number of variables in your code and keep related data together in one container. Accessing list elements is done with an index expression, using square brackets after the list's name. This lets you select the element at that position quickly and efficiently. Indexing starts at 0, so the first element is at position 0, the second at 1, and so on. You can also use negative indices to count backward from the end. The index must always be an integer. Python will raise an error if you try to use a float or another type, even if it looks like a whole number. On the slide, examples show how to access the first and last elements of a list of student names. This makes lists especially useful when working with collections of data like rosters, words, or items in a menu. Lists are mutable, so you can update them directly by assigning a new value to an element at a particular index. This allows you to change the contents of the list without creating a new one. Lists also have methods to add and remove elements. The append method adds a new element to the end of the list. The pop method removes an element at a specified index, while remove deletes the first occurrence of a value. These methods give you flexibility to grow or shrink a list as needed. The slide examples show how to update a number inside a list, append a new element, and remove elements both by index and by value. These capabilities make lists one of the most powerful and versatile data structures in Python. Sequence-type methods are functions that belong to sequence objects, like lists or strings, and are called with dot notation. Examples include append, pop, and remove for lists, which either alter the object or provide information about it. Sequence-type functions, by contrast, are built into Python and take sequences as arguments rather than being tied to a specific object. Examples include len, min, max, and sum. The important distinction is that methods are called on the object itself, while functions operate on the object passed to them. The slide examples demonstrate how to append to a list using a method, and how to use len on the same list to get its length as a function. Understanding this difference helps you quickly recognize when to use dot notation versus passing the object as an argument. Tuples are similar to lists, but they are immutable, meaning their contents cannot be changed once created. A tuple is created using commas, often surrounded by parentheses, such as 5, 15, 20. Tuples support sequence operations like len and indexing, just like lists, but because they are immutable, you cannot reassign elements after creation. Tuples are especially useful when the position of values matters, and the data should remain constant. For example, storing latitude and longitude as a tuple ensures that the values remain fixed and are always accessed in the correct order. The slide examples show how to create tuples, retrieve elements by index, and calculate the length. Tuples aren't as common as lists, but are important when you want reliability and unchanging data. Named tuples extend the concept of tuples by allowing you to create lightweight data structures with named attributes. Instead of accessing elements by index, you can use dot notation with descriptive names, making the code easier to read. For instance, a named tuple variable called car might have fields for make, model, price, horsepower, and seats. Accessing car.price is clearer than car2. Named tuples are created with the collections.nameTuple function, where you define the type name and field names. This allows you to represent complex data more clearly without writing a full class. On the slide, the example demonstrates how to define a named tuple, create an object, and access its attributes. Named tuples are particularly helpful for bundling related data together, while keeping your code concise and readable. It's important to note that the nameTuple function only creates the new data type definition. No data objects are created until you call the new type with actual values, such as car with inputs Chevy, Blazer, and 32,000. The resulting object's attributes can then be accessed with dot notation, which is simpler than remembering numeric indices. Like regular tuples, named tuples are immutable, so you cannot modify their attributes directly. To change a value, you must create a new object with the updated data. The slide example illustrates this by showing how to create a car object, access its attributes, and then replace it with a new object if values need to change. This immutability ensures reliability and consistency when working with named tuples. Sets are another container type in Python. They are unordered collections of unique elements, meaning that duplicates are automatically removed. Unlike lists or tuples, sets have no indexing or position, so elements cannot be accessed by index. Sets are created either with the set function or with curly braces containing elements. An empty set must be created with the set function, since empty curly braces produce an empty dictionary instead. Sets are often used when you need to eliminate duplicates from a collection or check for membership quickly. On the slide, examples demonstrate creating sets from a list, creating set literals, and handling an empty set. Sets provide powerful operations for ensuring uniqueness and working with collections of values without regard to order. Because sets are unordered, they do not support indexing like lists or tuples. Trying to use square brackets to retrieve an element by position will result in a runtime error. Instead, sets are most often used to reduce a collection with duplicates into one containing only unique values. For example, if you pass a list with repeated numbers into the set function, the duplicates are automatically removed, leaving only the unique values. On the slide, the examples illustrate both of these ideas. Attempting to access an element by index produces an error, while converting a list with repeated values produces a set with only distinct elements. This property makes sets particularly useful in situations where order does not matter but uniqueness does, such as filtering user IDs, removing duplicates in data, or checking membership. Sets are mutable, which means you can add or remove elements as needed. The add method inserts a new element into the set if it does not already exist. The remove method deletes a specific element, raising an error if the value is not found, while the pop method removes a random element. Sets also work with len to determine their size, and membership can be checked using the in operator. On the slide, the examples demonstrate adding values, removing them by name, and popping random elements. This mutability makes sets versatile for managing collections of unique items that can change over time. Combined with their built-in support for set operations, sets provide a rich set of tools for working with collections of data in Python. One of the most powerful aspects of sets is their support for traditional set theory operations like union, intersection, difference, and symmetric difference. These allow you to combine or compare sets in flexible ways. The intersection method returns only the elements common to all sets, while union collects all unique elements from multiple sets. The difference method returns items found in one set but not the others, and symmetric difference gives the elements that are unique to each set but not shared. On the slide, the examples show how these operations work with simple sets of numbers. These tools make sets valuable in practical applications like comparing datasets, finding overlaps between groups, or identifying unique elements. By using set operations, Python provides an elegant way to apply mathematical logic directly in programming tasks. Dictionaries are another major container type in Python, used to capture associative relationships. Unlike lists or tuples, where order matters, dictionaries map keys to values. The analogy is an English dictionary, where the word cat is a key and its definition is the value. Keys must be immutable types like strings, numbers, or tuples, while values can be any type. Dictionaries are created using curly braces with key, value pairs. For example, a dictionary called Players might map Messi to 10 and Ronaldo to 7. An empty dictionary is created with braces. Dictionaries are especially useful when you want to store data that has a natural association, such as names to grades, IDs to email addresses, or car models to prices. The slide examples show creating and printing dictionaries, illustrating how keys and values are paired. Dictionaries are mutable, so their entries can be added, modified, or removed as needed. A new entry is created by assigning a value to a key in brackets. If the key already exists, the assignment updates the existing value instead of creating a new entry. To remove an entry, you use the del keyword with the key, but attempting to delete a non-existent key will raise an error. On the slide, the examples show how to add a student grade, update an existing one, and delete an entry. These features make dictionaries flexible and powerful for representing associations. With dictionaries, you can maintain dynamic mappings between data elements, allowing programs to evolve as information changes while still keeping key, value relationships clear and organized. Python has a number of core data types that programmers use frequently, and it's important to understand the categories they fall into. Numeric types include int for integers and float for decimal numbers, both of which support arithmetic operations like addition and multiplication. Sequence types include strings, lists, and tuples. Strings are ordered sequences of characters and immutable, while lists are ordered and mutable, allowing changes, and tuples are ordered but immutable, preserving data consistency. Finally, dictionaries are mapping types, associating keys with values without any specific order. These categories cover the most common data structures students will use early in their programming journey. On the slide, the examples highlight how to define each of these data types and what they look like in practice. Understanding their strengths is the first step toward choosing the right container for your problem. Choosing which container type to use can sometimes be confusing for beginners, but there are general guidelines that help. A list is best when you have an ordered collection of data that may change over time, such as lines of text. Tuples are appropriate when you want an ordered sequence that should remain unchanged, like geographic coordinates. Dictionaries are the right choice when data has a natural association, like mapping student names to their grades. Sets, while not listed on this slide, are ideal when uniqueness matters more than order. The key to choosing correctly is to think about how your data will be used. Does it need to stay ordered? Can it change? And does it involve associations? On the slide, examples show lists, tuples, and dictionaries in practice, helping to clarify these choices. Type conversions occur when data is shifted from one type to another, often between integers and floats. This happens frequently in calculations. For example, if you compute 0.504 times a number of births, Python will combine an integer and a floating point value. Implicit conversions happen automatically when different numeric types are mixed. If either operand is a float, the result of the operation will also be a float. This means that 1 plus 2 evaluates to 3 as an integer, but 1 plus 2.0 becomes 3.0, a float. Similarly, 1.0 plus 2.0 produces 3.0. These conversions ensure that operations make sense and preserve precision. On the slide, the examples demonstrate these implicit rules in action. Understanding when Python promotes values automatically helps you avoid confusion when working with mixed types. Sometimes, a programmer needs to explicitly convert between types, and Python provides conversion functions for this purpose. The int function creates integers, whether from another integer, a float, or a numeric string, though fractions are truncated. The float function creates floating point numbers from integers or valid strings containing decimal points. The str function creates strings from any type, letting you convert numbers or other data into text. A common use case is handling user input, because the input function always returns a string. If you want numeric input, you must explicitly convert it to an int or float. On the slide, the examples show converting floats to integers, strings to numbers, and using str to convert values back into strings. These tools are essential for bridging the gap between user input, textual data, and numeric calculations. Binary numbers are the foundation of how computers store and process information. While programmers typically think in base 10, computers use base 2, with only the digits 0 and 1. Each digit or bit represents a power of 2. For example, the binary number 1011 equals 1 times 2 to the third plus 0 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0, which totals 11 in decimal. Variables in low-level systems are stored in a fixed number of bits, like 32 or 64, which limits their range. Python, however, allocates additional memory when needed, so you rarely worry about overflow. Still, understanding binary is critical in computer science, since it underlies memory storage, arithmetic operations, and how processors interpret instructions. The slide highlights the contrast between decimal and binary representations to illustrate this key concept. In this video, we explored some of Python's most important data types and how they are used in practice. We began with strings, learning about literals, immutability, indexing, and how to use f-strings with format specifications for professional-looking output. We then covered lists, Python's most versatile sequence type, and learned how to access, update, and modify elements with methods like append, pop, and remove. Tuples were introduced as immutable sequences, along with named tuples for clarity and readability. We also examined sets, which enforce uniqueness and support mathematical operations like union and intersection, and dictionaries, which store key, value pairs for associative data. After comparing these container types, we moved into type conversions, distinguishing between implicit conversions in arithmetic and explicit conversions using int, float, and str. Finally, we ended with a discussion of binary numbers, the base 2 system that underlies all computer storage and computation. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.